They're both going to speak for about half an hour on, well, 25 minutes and then 5 minutes of questions on anthropogenic fluxes and inventories. And then the last half an hour will just be a sort of a general discussion or allow time for a bit of overrun. So the idea is we're probably going to video this and post it on YouTube, just so people are aware. So if you do ask a question, you will be YouTubed. And without further ado, I will introduce Pete and say, off you go, Pete.
Thank you very much. I shall just share my screen if I can remember how. There we go. Is that going through?
Yep.
That's visible. Okay, I might just turn my video off just to preserve my bandwidth. 1 second. Okay, I shall begin. Okay, so I'm going to talk about anthropogenic greenhouse gas fluxes from the UK, mostly talking about modelling spatio-temporal variability and uncertainty associated with that.
People who are not talking, can you mute your microphone, please? Someone's tapping away.
It's got very noisy typing. Okay, so the background to this is that the UK has a commitment to reduce net greenhouse gas emissions to 0 by 2050. And I'm sure you're all familiar with the background to greenhouse gases and climate change and the rationale for that, unless you've been on a different planet. So that's why we're doing this. We're monitoring that change. So this talk is going to talk about 4 things, 4 little sections. I'm going to talk about the UK inventory, how we've actually gone about monitoring greenhouse gas emissions in the past and in the future. And I'm going to talk about temporal variation and spatio-temporal variation, and I'll try and explain why that's important. And lastly, I'm going to talk about how we might combine the inventory with atmospheric greenhouse gas observations on the tall tower network in a perhaps more systematic way than we have done previously. Okay, so since the inventory started in the 1990s, it's been contracted out by the UK government to Ricardo Energy Environment, which is a scientific consultancy company, does many things, with some of the sectors subcontracted out to other partners. So Rothamsted Research to the agriculture section, and CEH to the LULUCF, the land use change and forestry section, and some of the spatial mapping. And the inventory itself is based on a whole host of economic and statistical data for all the activities that result in greenhouse gas emissions that we can think of. And this comprises something of the order of 600 models of these different activities. And so there's numerous emission factors in there, but the basic modeling that goes on is generally of a simple form. So you have the amount of activity, which might be miles driven in your car, or the amount of megawatts produced by some power station, times the emission factor, which is especially how you convert that activity into an emission, and that gives you the estimate of the emission of each of these different activities, and we add them up to give a total. So this is where we are in the most recent inventory year. The inventory is a little bit behind real time because it takes time to add up all these things and get the data in a reasonable form. So you can see that in the current day, the largest CO2 emission is from transport. So that's the summation of all road transport and aviation and shipping and commercial transport and whatever. Followed by energy production from power stations, gas and whatever. And joint third is residential and business combustion. So that's basically gas burning for your central heating and hot water and whatnot, either in a domestic home or in a business. So it's all coming from essentially combustion of fossil fuels to generate CO2. Very small amounts come from cement production and some other stuff which is not designed for generally producing energy. like smelting iron ore, that sort of thing. So this is where it sits in the historical trend. This is the past 50 years of CO2 emissions since the inventory was being projected backwards this far. So largely over 40 years, it shows not much change. The orange band at the top was reducing as we moved away from heavy industry. But there's not much change apart from the general rise in transport emissions, which is the purple band at the bottom, which is basically the rise of car ownership and car use. In the last 10 or 15 years, you see a substantial decrease in emissions from energy production, which is largely the conversion of coal-fired power stations to gas, and the uptake of renewables. So the green band in the middle has come down substantially. So over most of the past 50 years, energy production has been the biggest source of CO2 emissions, and that's now come down such that transport is now the biggest source. If we just think forwards a little bit to the next 30 years to where we're trying to meet the net zero target in 2050, it shows the sort of challenge we face. So in order to get to where we are today, 365 teragrams a year down to zero, you need to reduce by 12 teragrams a year, which is a challenging target. The optimist might say this is relatively easy. We just need to keep doing what we're doing, because over the last 10 years, we've actually been reducing total emissions by 14 teragrams a year. Of course, the pessimist would say you do the easy targets first. You do the easy steps first that are low cost, and that leaves all the difficult things to do yet. So we need to continue moving towards renewables, and at some point, all the coal-fired power stations will be decommissioned. Probably in about 2025, there'll be a ban on new homes having gas boilers in them or any kind of fossil fuel burning boiler. And in 2030, we're due to have a ban on cars with internal combustion engines. So that purple chunk at the bottom should start declining. Quite how on target we will be by that time, who can say? But that's the prospect for the future. So should be substantial decreases in that big green band and in the in all those bands really. One major complication for CO2 emissions is that there are very large natural biogenic growth fluxes which go on every year. So the natural ecosystems take up a lot of carbon through photosynthesis every year and then emit it again over the course of the winter. So these are about an order of magnitude bigger than the anthropogenic flux, although of course they come around to a balance of almost zero. So we're trying to discern a signal above these background large gross biogenic fluxes. Okay, this shows the same kind of idea for methane emissions in 2019. These graphs are all on the same scale. They're all in teragrams of CO2 equivalents. So you can compare numbers like for like. So this shows that agriculture is dominated by two things really. By agriculture, that's mostly coming from livestock, livestock and livestock manure, and also still substantial emissions from waste, so from methane coming from landfill sites mainly. If we look at that in the historical context, we see that landfill is actually, the waste emissions have come down substantially over the last 30 years, this is showing, mainly with capping of landfill sites, more constructive things done with food waste and that sort of thing. Whereas the agricultural emissions haven't really changed, because that's basically a function of how many cows and sheep there are. And lastly, we come to N2O emissions in 2019. These are even more dominated by agriculture. Agriculture constitutes, I think, 75% or slightly more than that of the total emissions. Nothing else produces very much these days. Putting that in context, it used to be There used to be quite large industrial sources of N2O, but these have largely been reduced, mainly because it's an ozone depleting gas. So that was came under the Montreal Protocol, so things had to be done. It was legislated against much earlier on. So, a little summary. CO2 provides 80% of the total emission. In CO2 equivalent terms, methane and N2O provide 12 and 5% respectively, with a small contribution of hydrofluorocarbons. So the inventory gives us annual emissions, and it also provides uncertainties on those annual emissions. So for each of these sectors, it provides an estimate on each of them for what the uncertainty is on that annual emission, and you can see it's down at about 2 or 3%, 3 or 4% for most of the combustion sources, whereas in agriculture and LULUCF and waste management, the numbers are much bigger. So of the order of, well, tens of percent. So this inventory is accurate, essentially where the greenhouse gas emission is closely related to a traded commodity, meaning it's paid for in pounds and pence, and so we know how much has changed hands and how much has been used, and that is generally the case with combustion of fuel. However, there's uncertainty where this is not so. So in agriculture and waste and land use and gas leaks, the emission is a byproduct. It's not an intentional thing. It's not traded. It's an accidental happening that we have to quantify somehow, and that's much harder. So something like 65% of the uncertainty comes from a relatively small fraction, about 20% of the total emissions. The inventory also provides sector-specific maps. So for every 1 kilometre grid square in the UK, we have an estimate of the annual emission of all the greenhouse gases in that square by methodology, which I shan't go into. That's just an illustration. And oops, one going ahead of myself. And what it doesn't provide, however, is temporal dynamics within a year. So we don't know when the emissions occurred. It doesn't tell us anything about that. Nor does it give uncertainty in the maps. So the maps are given as red. There's no uncertainty associated with them. However, what we need to know for linking the inventory to atmospheric modelling is something about spatio-temporal variation and its uncertainty. I'll try and explain in a moment why that's important. But that's really the challenge for this part of the DARE project, is disaggregating the annual emissions into spatio-temporal estimates. So if I can try to illustrate why that matters. How the atmospheric inverse modelling works, as most of you probably know, is by running an atmospheric transport model. So this animation from Matt is showing the name footprints of the 5 tall tower sites in the UK over a period of time. And it's just showing where the air has come from, which is influencing the mixing ratio at that point. So that gives you the time series of that's producing the time series of mixing ratio concentrations in the graph at the top left. So fundamentally, that's some sort of interaction between the time series and the spatial maps that you see at the bottom. So there's a spatial variability in the emissions that we know quite well. And what you measure at the tower site is the interaction between where that footprint comes from. So what areas the wind is picking up. So what regions you're looking at, and how the fluxes themselves, the emissions themselves, vary in time. So what you need to know really to interpret this time series is not the uncertainty on the annual emission, but it's on the uncertainty on the emission at a particular place and at a particular time. So for example, what's the uncertainty on the emissions from Lincolnshire, from the agricultural emissions from Lincolnshire in April 2019? That's the key thing which you need to know in order to know how much weight to place on the inventory estimates versus your atmospheric modelling measurements. Just for another example, what's the uncertainty on the CO2 emissions from traffic at 11 o'clock on the 6th of June in a particular year. So that's the kind of things you need to know if you're going to use these measurements properly. Just to illustrate why this, whoops, gone on too far. Just to illustrate why the spatial variation is important, particularly for CO2, the emissions are quite strongly dominated by point sources, less so than they used to be with the closure of power stations, many of the old flat power stations, but the emissions are still quite point source dominated. So something like 40% of emissions comes from the point sources for CO2, and 20% of all the emissions comes from just 36 points. So power stations and a few other sites. It's less the case for methane and N2O, so they're much more widely spread, largely because agricultural waste emissions are much more widely spread. So it's less of an issue there, but they're still pretty heterogeneous in space. So let's first have a look at temporal variation. Oops, I've done it again. There we go. So how do we estimate how the emissions vary over time within a year? Well, there have been various projects doing this, mainly for modeling air quality, actually, in the past, which has summarized economic and statistical data of how these things vary over a year. So there's oops. There we go. That's it. So there are different modeling projects which have estimated these things over time, both in Europe and in the USA. But of course, what we want is actually UK specific data. We don't really need to know how it happens generally. We want to know how it happens in the UK. Well, let's first take a look at how good these previous data sets are from Edgar and EMAP and GENEMIS and MapAir. And they show some consistency, but they're not perfectly consistent. So they're useful as a prior source of data, but we want something more specific. So these graphs are just showing the variation around the mean on the mean diurnal cycle for each of the different sectors. So it's showing how, for example, domestic combustion is high in the morning and high in the evening, but people aren't at home during the middle of the day. So you see that characteristic diurnal cycle. And similarly with road transport, you have peaks at rush hour in the morning and the afternoon, but it's quieter in the middle of the day and at night. Without dwelling on these too much, this is showing the weekly pattern. So going Saturday to Sunday, there's busy during the week, quieter at the weekends. And there's reasonable agreement in the models as to how this pattern pans out. And lastly, the seasonal variation, again, some agreement, some measure of disagreement. But what we want is UK specific data. And for some of the sectors, that is quite readily available. This is some data obtained by my colleague Sam Tomlinson, which gives half-hourly CO2 emissions right back to 2010 for total emissions from the energy sector in the UK. So obviously we have some very good data with which we can estimate these patterns. And how do we do that? So the statistical method we've used is a Bayesian approach. So we're taking those previous data sets as a prior and taking whatever UK specific data we have to hand to feed into our likelihood function. The kind of model we're using to reproduce these patterns is called a GAM, a generalized additive model, which you don't need to worry about. Basically, it's some combination of splines and regression. So in the standard Bayesian pattern, we take that as a prior, use the data in the likelihood function, and that gives us a posterior distribution if we use an MC kind of algorithm. Details of that don't really matter for now. And what does that give us? So that's the purple splatter of points is giving us our posterior distribution. Sorry, the band is giving us our posterior distribution, showing the data around it, and our prior estimates before that from these other models. So we can incorporate the actual UK specific data against this background of prior data from these European generic data sets. So that works well for energy sector. We have something similar for the road transport sector, although we don't have the raw data, but we have very good summary data of how this pattern averages out across the UK. So we've done the same thing here. So we have the prior data superimposed on that, the posterior, done by the same method for UK traffic data. Lastly, we have something similar, but haven't got quite that far for the UK agricultural sector. This is some work done by my colleague Carnell, also at CEH, who's gone into minute detail of how all the subsectors within agriculture vary over a year. I don't know if you can actually read the labels here, but it's all the different subcategories of agricultural activity, such as manure spreading and leaching and whatnot. And this pattern is coming from largely from application of fertilizer in the spring and manure spreading in the autumn. So that's data we can use in this same procedure, although we haven't got quite so far with the agricultural data. Now that's temporal variation within a year, but what we really need, as I tried to explain earlier and probably failed, is what we need to know is how these temporal patterns vary in space, because that's what the data at the tall towers is picking up. That's the signal that we're trying to incorporate. So we need to know how these patterns vary, say from Northern Ireland to southwest of England. Do these patterns show the same thing? And there's very, very little direct data on that, almost none in fact. So what we need is some kind of proxy. So one way of doing this is not to use direct measurements of the activity itself, but to use something which acts as a correlate of that, or a proxy. And what we do have in the UK is very good air pollution monitoring networks, which have been running for quite a long time. So this map on the right shows the automatic urban and rural network of pollutant monitoring, which has been running since 1990. And over that time has run more than 350 sites. So there's something like 42 million records since 1990, which are available to use. Now, it doesn't tell us anything directly, but we can assume, well, we know that production of many non-greenhouse gas air pollutants is related to the same kind of activities as we've been talking about, agriculture and transport and energy production. So we can basically stick them in what's basically just a big regression equation. So the beta term is the contribution of each sector to emissions at each location. I'll come back to that in a moment, against simply the concentration or the mass density measured on this network for each of these 6 gases. And I picked these 6 gases because there are good records available and we know how we think they're emitted. So that we both know their emissions and their concentration measurements. So let's just think about the beta terms there. That's this map is showing the contribution at each location of each sector to the emissions of, in this case, carbon monoxide. So depending where in the country, the sector which produces most carbon monoxide will vary depending where you are. Simple example, if you're in the sea, there aren't many sectors contributing, but except shipping. So other transport is your main contributing sector of carbon monoxide at that location. If you're in an urban area, you'll have rural road transport emissions and domestic combustion emissions, etc. And we can do that for all 6 of these gases. So we know, fortunately I can't see the top of my screen, so I can't see which ones I'm showing you. Anyway, we have these maps for all of these 6 gases. I'll just run through them. And then we just plug those into that equation. So at each of these locations where they're measured, we know the local contributions of each of the sectors to this index. And does it work? provisional results suggest, yes, it works pretty well. For agriculture, this is showing that pollution index over the course of a year for agricultural emissions, and it's showing very closely what we expect them to be based on the inventory work. So this is signal largely driven by ammonia concentrations, and it's looking very promising as it does actually reproduce these things. This is showing the same thing, but over a diurnal scale for all the sectors except for agriculture, which we have to treat slightly separately. And that shows it's reproducing what we expect the patterns to be pretty well. Some variations, that curve in energy production in the middle of the day is not quite what we expect, but it's looking quite promising. So since we know this, each of these sites is actually giving us the spatial-temporal dimension, because we can interpolate from this range of sites to the whole UK, still using a GAM kind of model. And that means we can predict the emissions with spatial-temporal uncertainty. That's better illustrated than explained, I think. So this is what the kind of thing it can give us. So every line here relates to one of these sites from the network, and that's giving us the seasonal variation in carbon, and I can't see the top of my screen, so I can't see what gas that's showing.
Same domestic combustion thing.
Domestic combustion. Thank you, Alistair. Thank you. I don't know how to get rid of the. There's a banner from Zoom at the top of the screen. I can't seem to get rid of it. Oh, hang on. Hide floating controls. That's it. Domestic combustion, it says. Okay. So that's giving us not just the temporal variation, but how that temporal variation varies in space. And assuming it varies as some smooth function in space, we can model that with the GAM. Now, without dwelling on this too much, we can do this for industrial combustion for the same thing. We can go through all the sectors like this. So it tells you how it's varying in space and time for each of the sectors. I stuck plenty of slides in just because they're there, but there's actually the variation over the course of a week and in space for industrial combustion, non-road transport, and in road transport over the course of a week. So the weekend effect is bigger in some places than other places, and this is a way of quantifying exactly that. And lastly, I'm going to move on to how we might apply that to spatial temporal modeling. Sorry, how we apply that spatial temporal model to inverse modeling. Okay, so the idea for most inverse modeling approaches is that we have the name footprint that Alistair and friends run, and that gives us the footprint for a point, let's say the Billsdale Tower. And the spatial temporal model tells us, that's the map on the left, how that is going to vary in time. And the product of these two things is essentially your prediction of how the mixing ratio will change. So that's the map on the left is telling you how the flux varies in space and time. The footprint tells you how much that's going to contribute to that measurement point, and that gives you a predictive model, which tells you how you expect the mixing ratio at that tower to change over time. This is just dummy data on the right. Now, the conventional approach is taking the maps, the annual maps that the inventory provides as a prior, and then you update the map of emissions at each time step. But what we can do with this spatial temporal model is, because that predicts at each time step, we have a predictive model which we can then update the parameters of that spatial temporal model based on all the data that went into the inventory in the first place and based on the observations of the mixing ratio on the tall towers. Why is that a better approach? Several potential reasons. Firstly, simply there are fewer parameters to estimate. Now, exactly which parameters of that model you estimate is an open question, but it could simply be one which is an emission factor of interest, or one per sector, so you can vary each sector individually, but at the same time, however. But you're still looking at a fairly small number of parameters there, whereas if you're updating a whole map of emissions, you essentially have one parameter per grid cell. So you're vastly reducing the number of parameters in this way. Perhaps a more important reason is that it represents the system in some way, because it understands that emissions of multiple gases are all linked to the same activities. So you're effectively borrowing strength from the fact that combustion emits both carbon dioxide and carbon monoxide, and under some circumstances, NO2 and various other things. So it's incorporating prior information about the system into the whole process. And it's also incorporating the fact that we know something about the temporal pattern of activity in each sector. And that's something which is generally ignored in conventional approaches. So it's using that data in a sensible way. And lastly, the interpretation is perhaps more direct and easier. So rather than just two maps from two different methods, it's a way of actually updating the emission factors that are actually used in the inventory model, or at least allocating different sectors based on all that information. So, in attempt to summarize what I've said, there have been large changes in emissions in the past, and we're anticipated to have even larger ones in the future in order to reach the net zero target in 2050. In quantifying that, both the inventory and the atmospheric model, inverse modeling will both play a role, I think, because they're good for different kinds of emissions. To get the inverse modeling method to work properly, we need information on temporal and spatial temporal variation. That's critical to linking the two together. One way of doing that is by using non-greenhouse gas air pollutant data as a proxy, because that tells us something important about the spatial temporal variation. And taking that a step forwards, that spatial temporal model itself provides a framework for linking the two things together, for providing the inventory to the inverse modeling approach. And that's me, I think. Yeah. Thank you very much.
Thank you very much, Pete. Excellent talk. Thank you. Has anyone got any questions before we move on to the second talk? If people have got their hands up, let's see. Matt has got his hand up. Oh, several hands up.
Hi, Pete. Great talk. Yeah, so I've got a few questions. I mean, the first one, perhaps I missed it because there was a lot of noise here, was about when you're using your air pollution data to estimate these scaling factors, are you accounting for the influence of meteorology on those air pollution concentrations?
No, not at all. The only way I get around that is by averaging a lot of data, so that I'm assuming that over, I mean, sometimes because it doesn't matter, over a week you can average it all out and it doesn't matter. But you're averaging all the Sundays and all the Saturdays and it comes out in the wash. You're right, it's potentially an issue over seasonal and diurnal timescales. I just did this as a first cut to see if it worked, and it actually seems to work without worrying too much about atmospheric modelling. You're right, generally that's what we should do. It's just there's an awful lot of sites which we would have to do some rather awkward transport modelling to do it properly.
Well, I'm wondering if there might be some simple meteorological indices you could also include in your regression, maybe.
That's true. Yeah.
Yeah. Okay, I'll let other people ask questions. Thank you.
Thank you, Matt. Uta, nice to see you. Sorry, we can't hear you very well.
Okay.
That's much better.
That's better. No, it's not.
That's not better. No. Do you want to type it in the chat, Uta? And we'll come back to that after. I'll get Angelina to ask her question, then we'll come back to yours. Probably the best. Okay. Angelina, the floor is yours.
Angelina, you're on mute.
Very good. Thank you, Peter, for the talk. It was very interesting. I was wondering, how do you account for, let's go with recreational usage of N2O in the inventory? Like how is the use of the little canisters accounted for? Does that go under industry normally because it's used in restaurants, or?
I have to confess, I just don't know.
Okay. This is the
interesting question.
Insignificant source of N2O in Bristol. So we were wondering how it's accounted for in the inventory, because it would be interesting to see. Yeah, in general, we would like to know more about it.
I think that was something that was never thought of when they dreamt up the inventory categories.
Well, we were just wondering if it's like the sale of the canisters that will count as the emission factors, or if there's like, how is it?
If it's traded in pounds and pence, then it should be picked up in the inventory. Exactly which class it would come under, I don't know.
Okay.
That would be a tricky one to classify, I think.
Okay. Thank you. Right, we can go back to Uta's question. So I'll read it to you, Pete. It's in the chat. I like the idea of using other networks, i.e. the N concentrations to the greenhouse gases. It would be interesting to compare certainly for N2O the emissions using, I don't quite understand that question, using IPPC tier 1 approaches. Can you read that question in the chat, Pete?
I can read it, but
complete enough to, I can't really pick out.
I don't get the question, really.
Uta, can you have another go at that? And I also see that John Watson's got his hand up in the chat, so I'll move on to John, and then we'll come back to someone else.
Great. Thanks, Alistair. Can you hear me all right?
Yes, yeah, go for it.
Good. Zoom behaving. I'll come to the question from Angelina first, actually, which I think was about N2O used in, was it food type applications such as a foaming agent in?
Yes.
Okay. Yeah, it will be in the inventory. I suspect it will. Yeah, I'll find out which category it's included. I can't remember off the top of my head, but there's no problem getting an answer for you on that one. It is in the inventory.
Okay.
I can tell you, because I remember when it was approximately when it was included. There's other small sources of N2O as well, such as anesthesia as well, but they're pretty minor. The big one that Peter correctly identified was industrial emissions, which were substantially reduced following abatement at the Picken nitric acid plants, and indeed because in general some of them have shut, then it's now much smaller than it used to be. Pete, can I just ask you a question? Thanks for that presentation. I really like that. I thought it was great. For your emission factor of CO2 back from 2000 from large point sources, you calculated it on a half-hourly basis. I'm guessing that you've calculated it based on the reported, was it the generation from large plants, which they report, don't they?
Yes,
regularly?
that's right.
I thought you'd done that.
Yeah, they report the wattage that they produce.
Yeah, they report the wattage.
So you have to back calculate the emissions from that. Yes.
Yeah. We had a go at this a while ago. What fact did you just take a weighted factor and apply it to the overall wattage being generated?
Yes. So I just took the total from each year, the total wattage produced in each year divided by the emissions reported for that year, and back calculated what the bulk emission factor must have been.
Yeah. Okay,
So,
that's helpful. Thanks. Thank you, and thanks also for highlighting that. Was it 36 large point sources are about 40% of the total CO2? Yeah.
Well, it used to be much larger. It used to be something like 7% just came out of DRAX in the days when that it was.
Yes, well, things have changed. DRAX, of course, now is burning significant amounts of biomass, and that's estimated, but it's not in the national total. It's sat in a memo item underneath the totals. You'll find it, but not in the national total. That's CO2. Thanks.
Okay, thank you very much for the questions. We ought to probably move on to Hugo's talk now, and then we can come back to more general questions after Hugo's talk. So can I welcome Hugo, and the floor is yours if you want to share your screen.
I'm going to try to do that. Should be this one.
And Pete, there are some more questions in the chat if you wanted to think about those.
Okay.
So people can mute their microphones again.
Could you confirm that you can see my screen?
Yep, that looks fine.
Yeah,
looks good.
Because always lost in the two different screens, so I'm not always sure what people see. So good afternoon, everyone. It's my pleasure to introduce you to the work that we do at TNO, Applied Science Institute in the Netherlands. And I'll be talking about anthropogenic emission inventories with a bit of a focus on the greenhouse gases, but we very much integrate the air pollution and the greenhouse gases. I'll show you something about construction and trends and verification, and I do that really also on behalf of the people I work very closely with at TNO. So Stijn Dellert, Jeroen Kuhne, Ingrid Super, and Anton Visserdijk. And I thank them very much for already contributing for quite some time. I'm assuming not everybody will familiar with this, I will give some more generic introductions and then come to a few points that I think are relevant for Europe, but also for the UK. So our history is that in the 90s, we were co-developers of the EDGAR database, now at GRC. But in around the 2000s, that shifted really to a more focus on European air quality, and especially trying to make what we call generally model-ready emission data. So this is very much in line with what Peter has been showing. You get annual total emissions from agencies, but as a modeler, you need to know where and when it is emitted. So I've been working a lot on that, and especially in more and more collaboration with the air quality modelers, giving us very important feedback. So it's not one-way traffic. It's actually, we really need to get information back from the models, who then compare with observations, and from that we learn how to further improve. That has been very successful, I think, and has evolved also in an important role in the Copernicus Atmospheric Monitoring Service. I coordinate the emissions project in this, we generally refer to it to CAMS, but this is an important European service where you can find a lot of information. And since 2015, there was a change, because then we had the Paris Agreement, and that really pushed also funding for doing more greenhouse gas related research, and also in terms of making this kind of emission maps. And we're doing that in a number of different Horizon 2020 projects, and most notably the CO2 Human Emissions Project, or generally referred to as CHE, the Verify project, and the follow-up of the CHE project, which is CO₂, which has just started this year. Something that I won't be talking a lot about, but that we are actively pursuing at the moment, is the use of Earth observation data. It's really from the last couple of years, especially since Troponin is flying. That's a very interesting source of information, but I decided to really focus on the inventory work that we're doing. And for that, I take a quick step back, and this will be familiar to everyone, so I'm not going to explain it very much. I just want to point out that this is the CO2 concentration at Mauna Loa, Hawaii, the famous graph, and it's just continuing. There is no, you don't see any hiccups. It's a continuous line. So there seems to be, yeah, really looks like business as usual, and I think that's important. And then if you take the global CO2 data from EDGAR, you actually see pretty much the same thing, with only a small hiccup in around 2009 due to the economic recession. But so that's looks like nothing is happening, but that's far from true. A lot is happening. When you decompose that graph, and again, this is data from the EDGAR database, you see very interesting patterns. So I really broke it down in only 5 major groups. So you see India and China in orange and red, and they're really changing. And in blue and green, you see the US and EU plus the UK. And you see them sort of gradually declining a little bit. And you see also the rest of the world in gray growing very rapidly. So this emission landscape is very rapidly changing. And we really need to take that into account. We need to look how it, you know, it's all fine if we try to solve our problem in the Netherlands or in the UK, but if you look at this graph, you know that that will be a rather trivial success. So we really need to do our work as best as we can, but we need to really think also how can we export it and how can we bring it to other regions to really support the Paris Agreement in making some changes. I think that's important background. And then if I jump to what we do. So on the one hand, you have the kind of bottom-up emission inventories, rather classical, exactly following what Peter just explained. And EDGAR is another example of that on a more global scale. And what we tend to do is what I generally call hybrid compiled inventory. We collect various different bottom-up estimates, even possibly including some expert judgments. And we do that because on the one hand, as Peter has shown, there is already an enormous investment in the inventories in different countries. And when we try to combine that for the whole of Europe, there are like, I don't know, let's say 30 or 40 countries. Many of these countries already invest more in their inventory than we could invest in the European scale inventory. So if we're smart, we just try to pick that up and then compare, intercompare, and gap fill where needed, and in that way make a more complete product. Also, of course, the UK, the Netherlands, they have very nice high resolution gridded inventories. That's not the case all over Europe, and we want to make everything in a sort of level playing field, having a consistent map. So how do we do that? We take up these official reported emissions, for example, from UNFCCC and the CRF forms. We also take up the air pollutant emissions as reported to EMAP, and we combine that with other emission data sets like GAINS or EDGAR, and we make internal bottom-up checks for uncertain sources like residential wood combustion or inland shipping, agricultural waste burning. All of that we bring together in this little blue box, which is then a big database with emissions for all kinds of pollutants, split over 80 plus source sectors. And then we distribute that over the map using spatial proxies that we sometimes pick up as they are, sometimes especially develop using different information sources. So think about urban population, rural population, road transport intensities. For example, we also used to make our own shipping grids, but in CAMS we now work together with FMI from Finland, and they make much nicer shipping grids than we used to make before. So we easily adapt, and now we take up their product. All of that together then amounts to this gridded European regional emission product. in a kind of map at roughly 6 by 6 kilometers, as you see above. And of course, it's also a time series. So in the bottom, you see an example of the emissions going from 2000 to 2018, in this case for NOx emissions. So when we have all this information as a starting point, we can then try to start and look into verification and attribution of CO2 emissions. So one thing that we need to look at is the consistency across scales. So when we move from one country to another, but also when we are within one country. And we really need other information because as you all know, CO2 is very long-lived, very well mixed. We need to be able to separate it. So indeed, we can use the co-emitted species like NOx and CO, which are shorter lived, and we know how they vary from source sector to source sector. But we also need to take really into account the change in the use of biofuels or solid biomass like wood, but also biogas, biofuel and transport sector, because that's also shifting over time. And then there's a very important component of spatial distribution, and I'll show you some of what we do there. There are other really important steps. As you know, the reported emissions lag behind, usually almost 2 years. So one important thing is to make these inventories closer to the present day. And then indeed the temporal emission profiles and uncertainties that Peter has introduced. We work on that as well, but I will not be showing that in this presentation. My colleague Ingrid Super will give a presentation in this seminar series in June, and I'm sure she will pay more attention to these 2 points. So when we look at the scales, we have the global scale, so that's the EDGAR database, and then we can nest our emission map in that global scale and try to make that connecting. That's not so easy. It's actually quite a lot of work because they're very different. This is one of the downsides of our let's say, hybrid approach. We don't know the deepest level of detail as it is done in every country. So sometimes this is challenging to explain where the differences come from, but still this is important. But in Europe, we can do it quite well. For example, we developed a 6 by 6 kilometer. We moved to a 1 by 1 kilometer map over a certain area of Europe for case study region in these Horizon 2020 projects. I'll show you a little bit later on what we do with that. But if you have that, we can also even nest a certain city inventory in it and try to connect the different information. That looks quite simple. It is often quite difficult because often source sectors are not exactly the same, or they're defined in a different way, or a city inventory can decide on excluding certain source sectors because they think they're not really something they have to manage. So that can be quite challenging, but it's also quite rewarding. And this approach is being used in the CHE project, where we then model at different scales and try to understand well, the patterns that we see in the greenhouse gases. If you look at that, as I said, we make a time series, and of course we try to have the CO2 and the NOx or the CO in exactly the same way. So here you see an example of 2 of these maps. So on the left-hand side, road transport exhaust diesel from CO2, and on the right-hand side from for NOx for the same source. And of course, you can do that for all source sectors that we have included. I'm not going to do that. I just like to show you, for example, the shipping. So this is the international shipping over the European domain, also the CO2 and the NOx. So we can really break this down and provide it in such a consistent way to modelers who can then take that up in their well, either for comparison directly with observations or in an inverse modeling framework. Yes. What is interesting and what I like to show to you is the trends that we see over these time series. So what you see here on the left-hand side is CO2, and there are actually two CO2s there. One is from the biofuel, and when I talk about biofuel, I also mean solid biomass, so it includes wood. And you see the fossil fuel CO2. If you just look at that graph, you can already see two things. One, CO2 from fossil fuels is gradually declining a little bit, but the other one is slowly increasing. So the biofuel is partly compensating for the loss for the reduction in fossil fuel. Then when you look at co-emitted species, I have there 3 species listed. So CO from biofuels, so that's mostly from residential wood combustion. That's rather stable over time. And then you see the CO from fossil fuel combustion, mostly coming from road transport, shows a very strong decline. And also NOx emissions over time shows a very strong decline. So you can already from this graph, and I will not give you the details by source sector, but you can already see that it's quite challenging in a way to use these co-emitted species in a longer time series, because the ratio between the emission of CO or NOx and CO2 is constantly changing. And it's not, you know, it's even in a time frame of 5 to 10 years, the changes can be significantly different. So we really need to account for that. And this is, well, this is what we try to do, but it's something that really should be taken into account when we combine these things. And then when you look at the European map, and I think that's interesting, as I said, you see here that the CO2 from biofuel is increasing, but really it's also a very diverse picture over Europe. So here you see the share of anthropogenic CO2 emissions from biofuel as a fraction of the total. So you can see that there are countries all the way to the right that have like less than 5% of biofuel CO2 emission, but there are also countries that are well above 30 or 40% in their total CO2 emissions. So this becomes very important if we want to use a network over Europe and we want to understand the CO2 that we pick up there. We need to be very much aware of that this can be really changing dramatically over the whole domain. And of course, we expect that this is actually getting a lot more complicated in the next 10 years, because there are very strong targets accepted for 2030. And one way to achieve those is to replace your fossil fuel with biofuel. But we really have to scratch our heads around this, because in the end, it's about the CO2 concentration in the atmosphere. And we should really wonder if this is the solution that we should see here. As I said, this change over 10 years time has a spatial component, and that's also that's what you see here. Especially you see an increase really over Central Europe, also in the UK, but for example not in France, and that is because France uses a lot of nuclear energy, and much of the increase over this 10 years period is also the additional burning of biofuels in, for example, coal-fired power plants to reach greenhouse gas targets. So we see very complicated pictures in a way over Europe, and it's difficult to generalize. Then I want to go to the point sources, which if you look at the European domain and like was shown by Peter, they are really important. And what you see here is the contribution of point sources to the emissions of a number of pollutants. So the co-emitted species, CO, NOx, PM2.5, SO2, and then these biofuel and fossil fuel CO2. And you can see that actually the contribution from the point sources is quite similar for these two types of CO2, if you like. It's around 50%. So that's very important. These are all point sources. And we we try to combine them from different information sources that we can get. So there is the European Pollutant Release and Transfer Register, EPRTR, and there is the Large Combustion Plants Directive. And then we also use other data sources. This was recently presented by my colleague Stijn Dellert at the ICOS Science Conference. But there are some interesting things. We found out that we can really make some large improvements there. So what you see in this plot are the number of plants reporting emissions in the EPRTR. And you see a total, that's the orange line at the top, and then you see the individual species. And you can see there's a very large gap between the total plants reporting and each of the individual pollutants. And that is because not every plant reports every pollutant. And this is pretty tricky, because it can mean that a plant that reports CO2 may not report CO or NOx. So you can have CO2 emissions without NOx emissions. And for this, we try to correct. And we do that using a large number of information sources. But it's also important to explain why this is actually happening. And that is because of the threshold value in the reporting. And you see that table on the right. And to make it very simple, that means that if you have a plant that emits CO2 above 100,000 tons per year, it will have to report. But if it reports, for example, NOx below 100 tons per year, it doesn't have to report NOx. So you can see that, especially when you go to not the major plants, but like say the medium-sized plants, this creates a lot of gaps in that data set. And so this we try to fill. And it's, well, we have a saying in Dutch, which is, it's monk's work. So it means it's a tedious and time-consuming job, but we managed to make quite a well, impressive change here. And this really makes our gridded data set a lot more valuable because we now have this matching of the co-emitted species with the greenhouse gases much better. And this map shows a little bit what the final result of that is. All these little green dots are small point sources where we made a change in we gap filled one or more species. If you look at the large big red blobs, they are dominating the picture. And so the major CO2 emissions were really in the data set already, but not always with the associated co-emitted species. So this is a major improvement, and we really want to continue on this way because we think we can really change the kind of data. And this is an example of how we then use that kind of information. It's a very full slide, so don't panic. I'll try to say what I find really important. This is a collaboration we have in the Verify project and results from Samuel Hammer and his team in the University of Heidelberg. And what you see on the left-hand side are measurements of CO2, CO, NOx. And then the blue, I'm not sure if you can see my mouse, but the blue area here is an observation at the tower in the right-hand picture during a moment that the wind was not coming from the coal-fired power plant that you see depicted here in that plot. And the red is a moment in time when the wind was directly coming from this coal-fired power plant. And since they also measured 14 CO2, they could actually determine what share is coming from the coal-fired power plant. And then we can try to use that to compare with the emission, that is emission inventory that is depicted on the right-hand side. And when we do that, we actually find well, quite some discrepancies. So this in situ observation NOx to CO2 ratio was really much lower than what we had in our inventory. And for CO and CO2, it was much higher than what we had in our inventory. I'm not going to, at this moment, solve this riddle. I mean, it was really about, we need to revisit then the inventory and the scaling that was done. But this collaboration with people who do this kind of direct observations is very fruitful for us. at this same case study, we also noticed that actually we need to be very much aware when you have an observational station that some of these small power plants or that can be below the thresholds can, if they are in the vicinity of such an observational network, they can be very disturbing. So very close to one of their observational stations, there was a relatively small power plant completely burning on biomass. So it's not reporting its CO2 emissions because they're short cycle CO2. And with its CO and NOx, it was below the threshold. So we actually hadn't noticed it. So we need to very carefully think about what we see. Then I'd like to give an example of how all these data with different resolutions is actually being used currently. So this is a result from the J project, where you see on the top left, you see our highest resolution emissions being used by the Cosmo greenhouse gas model from Dominic Brunner and his co-workers. And then you go down, you see it with when they use the 5 kilometer resolution grid. And then you see it in the bottom where they start to use the EDGAR emissions, and top you see the global system that uses EDGAR emissions and a 9 kilometer resolution. And what you can see, without making it very complicated, you can see these individual power plants, they're actually disappearing as you go around this set. So what we are learning here is that resolution is really very important, and that we need to be at this below 5 kilometer resolution if we want to identify our power plants in Europe in this kind of system. So we're now working on trying to improve the input in this system, also for the more global scale oriented approaches. As the last thing, I would like to show that we're also really trying to verify this, and for this I wanted to make a small excursion to methane. We did a study in the Netherlands for the Groningen gas field. We are, like the UK, one of the big gas producers in Europe, and this was a study led by Tara Jakovic from Aerodyne Research, and we collaborated on that. And I'll go through it very quickly because I think it has also some interesting messages. So what you see here is actually why this question arose. The biggest natural gas producers in Europe have the lowest emissions. So you see the Netherlands, you see the UK, and we're relatively low emissions reporting from this sector in the CRF form. So, and the question, and this is why, of course, these Americans came in, they're actually challenging that. They're wondering, is that really true? Because they did a lot of measurements in the US, and every time they do that, they find out that the emission is underreporting. So we had this multi-scale coordinated approach in this area in the Netherlands, aircraft measurements, mobile measurements, and we contributed with downscaling our emission inventories, and we used ethane to methane ratio to make a distinction between oil and gas related emissions and, for example, agriculture and waste, which is very important. And if you were not aware, so these agricultural or waste management, they don't have ethane coming together with the methane emission, but the oil and gas always has a fraction of ethane. And in our case, that ratio is roughly 3%, and you can measure that around several of these sites. So we use that, and you can see the impact. So we use that to distinguish between the agricultural, mostly the livestock, and the oil and gas sites. And I can explain in more detail if that's necessary, but just to show you the result is basically how complicated this is in the end. We see here on the left-hand side, you see the emission map from the Netherlands, and on top you see actually the aerial that was area that was covered by the campaign. And that means we need to downscale or redistribute the whole emission map to this level and assume that it's proportional, but we're not really sure about that. And what we found during this campaign is that if you look at the regional mass balance, the inventory would say it's 14 micrograms per hour, and the observation says it's substantially lower. On the other hand, when we try to do this attribution to the different source sectors, we found that from the inventory, we would have guessed it's 2% coming from oil and gas. And whereas our best guess was that maybe 20% of the relatively lower emission that we observed was due to oil and gas. Unfortunately, we did not have enough of these ethane flask sampling in the plane. So the uncertainty that you see here in top of this 20% is really at the moment too high, and it's a snapshot, and we had the ambition and the hope that this would be repeated, but that's difficult. It's difficult to find the funding for this kind of campaigns when it's not compulsory to do it. So there were some key takeaways for me from this study is that validation of national statistics based on inventory approach on a sub-regional scale is really difficult. And for methane, I do think we can make major progress in the coming years using this kind of innovative mobile techniques and sort attribution. So there's the paper by Jakovic. There's also a very recent new paper by Hossein Matzahala from Utrecht University and also at TNO who did this in 2 European cities. Of course, we can also work on the satellite data, and we are doing that actually, but I will not show it today. So to wrap it up, why work on independent verification of CO2? I think we can assume that current inventories may not be sufficient to monitor the effectiveness of climate policies in the near future, and I think I've shown why that is happening. But it's already the case outside of Europe, and I'm sure also in Europe this will be true. However, bottom-up inventories with detailed source sector information, they will remain really key. So we need to actually strengthen them, and we need to very closely collaborate with them. So maybe that's the most important message, that we need observations, emission inventories and models, but they need to be connected, and we need to work very closely together. And with that, I would like to end and acknowledge the projects that we work on.
Thank you very much, Hugo. Excellent talk. Thank you very much. Particularly your last point that we all have to work together from inverse modeling to inventory modelers and between is a very, very important point. Has anyone got any questions? Let me just try and get to some hands up. I see a hand up from MGC. Sorry, I don't know who that is.
That's Morris Cox, I think.
Yes, I wanted to ask a question of the first speaker about statistical modeling. You use
You're on mute.
all right. Can you hear me now?
Yes, yeah, go for it.
A question for the first speaker. I enjoyed the talk very much. And it's to do with the statistical modeling and the use of priors based on previous data. How informative do you consider those priors to be?
Sorry. The uncertainty given to the priors basically comes down to how well the different models agree. So we have 4 different data sources. So they get high weight, relatively low uncertainty if all 4 models agree, and high uncertainty if all 4 models disagree. That's what provides the...
I guess another way of asking the question, if you had a totally uninformative prior, would it make a big difference? Can you say anything about that?
No, it would have very... If all 4 models disagree completely, or 4 data sources disagree completely, then the prior would be completely uninformative, be like using a uniform prior.
Thank you.
Okay, thank you. Any other question? Adrian Callahan, do you want to answer your question?
Hi everyone, sorry, it's me, Heather Graven. I'm just using my friend's computer. So I had a question for Hugo. Thank you very much for the nice presentation. It looked like you had a big change in your CO emissions in your revision. Could you say a bit more about what those emissions were from? And then if I could ask another question about the observed emission ratios from Heidelberg, if you considered whether those emissions are not just from the coal power plant, but from other emission sectors nearby.
Yeah, so indeed for the CO, if you how to say that in a correct way, but the reporting of CO by, for example, companies, the plants, the industry is very incomplete. It's dramatic. So they basically don't fill it, and I guess yeah, you may wonder who cares? Apparently, because it's going on for many years. So there is no real. So for CO2, you have to. You have this. You have to pay a CO2 price. You have to do these trading schemes and everything. So there's real compulsory to do that. For NOx, it's also much better because there is a lot of attention on NO2. But for CO, it's just undervalued, and there is no ambient air quality limit value, for example, that pushes legislation to report that properly. So they're not, yeah, they don't have to do it, and I think also they often don't know, but it's a big problem if you want to use the information from CO as a co-emitted species. So it's mostly the gap filling there that it was very, very incomplete. And then if you look at the trend, that's complicating, making CO even more complicated. There's a dramatic change in the CO emissions over Europe because of the improvement basically in the road transport sector. So that used to be the biggest source, and it's rapidly going down. So CO is actually a complicated piece of work in a way in this. And when you look at the more this case study area, I should say we're really busy at the moment trying to look into this more carefully. But you're very right. I mean, it means we find out that this is really tricky. You're at this one location, and you really should understand the let's say the emission and the emission sector and source sector landscape around these observational sites very, very, very well, because there can really be surprises. And one of them was, for example, this relatively small wood-fired power plant that, of course, if you are further away from Germany, like even if you are 200 or 300 kilometers away, it doesn't matter that this is sort of smeared out. But if it's within 5 kilometer radius of your observational station, it can have a massive impact. So indeed, you need to look into this footprint, and that's what they are doing. So what can come from other locations, but we realize, and this is what I think is very important, that generally speaking, the improvements can come from both sides. So we can make, when we have to rethink and so on, we usually find that we can still improve something on the inventory side. Also, the observational people realize that, oh, well, if that's the case, then maybe we should not use this, or we should exclude that. And that's really the way we are starting to better understand these data. I'm not sure if that answers your question.
Thanks, yeah. For the CO emissions, was it mostly then biogenic, like wood burning emissions that were missing? Or was it kind of a mixture?
Well, you have to understand, didn't explain that maybe very carefully. The difficulty is really the spatial distribution of those emissions. So they are being reported at the national scale as an annual total, but where are they really being, where should you locate them? That's difficult. And we use generic proxies for that, and we try to do as good as possible. But when you start to look into such a sub-region of a country, you can find out that there's a lot of, I don't know, guessing going on, like best guessing, hopefully, but that can really play a major part when you really try to understand, let's say, 100 by 100 kilometer domain or something of a relatively large country like Germany.
Yeah.
Okay, thank you.
Thank you.
Sorry, we ought to probably have a couple more questions. So John next, and then Ewan, and then we might be out of time. John Watson.
Hi, I'm just trying to get these controls to work in Zoom. Thanks. Just a quick one. I think it was Angelina who asked this, but the N2O emissions from N2O used in food use in the UK, just have a look in the chat. It's in category 2G3B in the UK inventory for your reference. If you have a look in the UK National Inventory Report, the Denier, you should find it discussed in there. Thanks very much for the talk, Hugo. It was great. I've just got one observation. Where you say that you think, or that people have said there's a bit of a mismatch between oil and gas production and emissions associated with that, it might be worth looking at the tier of methodology that's used to estimate those emissions. So whether it's a tier 1, a very simple method, or whether it's tier 3, much more complex, and just to maybe take a little bit of a deeper dive, it might be, and I'm just guessing here, that the higher emissions might be associated with the higher, the more simple tier 1 emissions. The other point that I want to make is that fugitive emissions from that sector are they're really tricky because of its complexity. I mean, there's huge amounts of pipes, systems, differences in extraction methods and so on. It's complicated. And the UK is actually investigating at the moment fugitive emissions from that sector. It's a very difficult area. Thanks. High uncertainty in it. Thank you.
Yes. No, thank you. Well, it's not about the tiers. I mean, it's a combination of things. There is something that annoys me a great deal, and that's there is too much confidentiality still in this reporting, because I don't know how it is exactly in the UK, but
yeah, there is
it's
some
companies
confidentiality, but
yeah, this is a nightmare because companies need to report, and they report in high detail. But it's then aggregated, and so the only thing that we can do is disaggregate it again. But that is, of course, highly uncertain. And the other thing is that what we do know is when we do real measurements, and we did that recently on the North Sea around the oil and gas platforms, that there is no correlation between the production and the emission. So, and this is indeed what you say about this fugitive emissions. So that makes it
very uncertain,
very complicated.
Yeah.
But therefore we need these ethane measurements. So if you measure methane and ethane, then you know what you're looking at, and that has to match.
Thanks, Hugo.
Okay, Ewan, thank you very much for the question, John.
Yeah, well, a quick one and then an observation. First for Hugo, it's not just ethane, of course. You could use the carbon isotopes using bag samples. So those flights are great, and you might fit a few more bags in your plane, because I know it's a very small plane. No, the wider question though was for both speakers. As I'm sure you know, last year methane went up by 15 ppb, which is the highest on record ever, including a terrible year in the 1990s. And if you look at the inventories in Europe, we're getting pretty good, and also in the United States, I think, at matching top down and bottom up. But in the tropics, it's terrible. Most tropical inventories are just guesswork. How do we propagate the work that you've been doing? And Edgar, I think, is fairly far out in much of the tropics. This really good work in Europe, how do we propagate that into the tropics? What's the simple, straightforward methodology of getting much, much better tropical inventories, especially for methane, where the tropics are so important in the methane budget. In CO2, you can more or less guess what's going on, but not in methane. So it's just a general observation. Think about it. I'm sure you can't answer that.
No, well, but I think it's I think it's a very good question, and that's also why I wanted to show this trend.
As we get up in conference,
because that's really going to be our biggest problem. That if we don't change things, we will know everything about a couple of countries that are very clean, and we know nothing about. So I fully support that point, and I think it's a huge challenge. My hope is partly on satellites, I have to admit, because that will give you a global view. But it's still very difficult because clouds can be terrible in the tropics. You probably know better than I do.
Yeah, especially the tropics. No, you can't see a thing. So.
And I think also there's one important thing, and that's that this is a blind eye, I think, I don't know if that's the expression, but from our funding mechanism. So I do European projects and I get funded to look at European problems. Of course, I try to do global, and we do it a little bit, but we don't do it by far enough. So I think it's also where you put your money, you get the best improvements.
So can we somehow put some pressure, and both in Europe and in the UK, on the governments to look at this? I have no solutions. I just
no. I don't have a solution, but we're happy to help. If there's any time a moment where we can do that, I'll be raising my hand.
Okay. Well, I think we're getting close to 3:30, so we ought to wrap up. Is anyone got any final questions to either speaker or some general comments at all? Matt, would you like to say anything at the end before we wrap up?
Well, just to say thank you very much to both speakers. They were two fascinating and really helpful talks. I think got lots to follow up on with both of you to kind of help formulate the next stages of the DARE project. So yeah, thank you very much again.
Yeah, thank you very much to both speakers, and all the questions that we got, and the discussion was excellent. Thank you very much. The next one, Aoife, is, I'm hoping you're going to dive in here and tell us when the next slot is.
Oh God, you really put me on the spot now. It will be advertised on the DARE UK Twitter page this week.
I won't put you on the spot any further. Thank you very much. You'll find out in good time, I'm sure, and probably should know already. Okay, well, thank you very much, and we look forward to seeing you again next time. There's one of these.
On the 17th of May.
On the 17th of May. I need to come good with you. Thank you very much.
Thank you, Alistair, for chairing.
Yes, no, cool.
Thank you.
Bye, everyone.
Thanks for the invitation. Bye-bye.
Thanks, everyone.